except when we want to be precise, we had those two caveats going. Well, what exactly does arbitrarily small mean, and what does sufficiently close mean, right? And so let's suppose that we have a function that's defined on that interval, right? On the interval from a to b, not necessarily at c, where c is some point between a and b. Right, then we had that the limit of the function as x approaches c equals L means, or is defined by, right, that the distance between f of x and L, right? So we can think about the distance function, or the distance between two numbers, being the difference of the absolute value, becomes arbitrarily small when x gets sufficiently close to but not equal to, right? And so when x is close to c but not actually equal to c, right? And so the notations that we'll use, right, are what we wrote down below, right? The limit is x goes to c of f of x equals L, or, right, if I write in arrow format or sentence format, right, I can read those arrows as either approaches or goes to. Right, and so we talked about ways of looking at limits, of being one-sided limits, right? And so often, right, when we're doing these approximations or estimations, especially in 2.1 and 2.2, right, the estimations, it was important to look at what's happening from both sides, right? So the limit from the left and the limit from the right, right? And then we can say that the limit in general, or the general limit of the function, is equivalent to saying that the limit from the left is equal to L and the limit from the right equals L. So if both of the right-hand and left-hand limits agree with each other, right, then that's the same as saying that the limit of x goes to c of f of x equals L. Right, and we looked at an example with approximating those here with that function x squared minus 1 over the absolute value of x minus 1, and that's where we finished off the last time. So switch over. Oh, that was the okay, switch over to the PowerPoint that I can write on. And let's start off just by kind of going through and doing another example problem. And this is one that I'm going to pull from the text. Oh, give me a second here to get it clipped over into the All right, and so this is a set of problems from the text. You have homework problems on the MyOpenMath that are relatively similar, not exactly the same, but kind of have the same type of flavor that ask us. They give you a graph and then ask you to go through and calculate some limits. All right, so right, this bit here, or these problems here, are asking it slightly differently. The instruction set didn't get copied over. Okay, and so this set of problems says in the following exercises, consider the graph is given, right, y equals f of x, right, and then tell me whether or not, say whether or not these are true or false, and if they're false, explain why they're false. Right? So problem number 46 here, right, asks us to look at the limit as x goes to 10 of f of x equals 0, right? And so once again, all we have is that kind of imprecise definition, right? Not actually a way to calculate this. We don't even have really any theorems that can help us, but we can use that rough definition in our intuition to think about what's going on. And just happened to my pen. And when I look at limits, I like to think about my limit as like I'm like a person, right, that's walking along my function. And I'm either walking along the function from the left-hand or right-hand side to where I'm supposed to go. So this person is supposed to be going towards 10, right? And both from the left-hand side and the right-hand side, right, it looks like I'm going to that point, right? The solid point, right, or filled in dot, right? And so that filled in dot, once again, that means that the function is defined to have that value. So both sides, it looks like that limit's going to 0, right? That's what they tell us here. And so that first one there, I would say is true. And if I look at problem 47, it asks me something about the limit as x goes to -2 from the right-hand side, right? So that plus means I'm only looking at it from the right of my function. And so if I look at -2 from the right, right, I'm on this part of the function. I'm going -2 from the right. That looks like that's going up and up and up. That does not look like it's going to 3. If I approach it from the left-hand side, it looks like I'm going to 3. But from the right-hand side, right, it looks like we're becoming larger and larger and larger. And as we will see in a minute, that gives us kind of it looks like could say that the limit, right, so that would be a false. Right, it looks like the limit is, let's just write the word false. Right, with my explanation being that the limit x goes to -2 from the right of f of x, right, looks like it's going off to being a big positive number, or we might even say positive infinity. I'll talk about limits being positive and negative infinity a little bit more here in a bit in 2.2. But right, that's what it looks like we have going on there. We could also, right, if we wanted to say, well, where are they getting the 3 from, right, that's really about the limit from the left-hand side at -2 of my function. It looks like it's going to 3, right? So either have one of two things. Either the 3 is wrong, right, when I'm approaching from the right, or I can change it to approaching from the left, and then it looks like I'm 3. But the statement itself, right, as it was originally given, is going to be false. Right, 48. Right, limit as x goes to -8 of f of x is equal to f of -8. Now, here they don't give me a value, but we see we have this situation where, right, it's got a open circle there. Remember, an open circle means I'm not defined at that point, or that's not the value of the function, right? The value of the function is given by that closed dot. So either the function isn't defined there, it's defined at a different point. So once again, right, 48 here has a problem because the limit here, whether I approach it from the left or the right, those both look like they're going to that open circle, which is at -6. So the limit is x goes to -8 of f of x. It looks like it should be -6, right? But f of -8, where the function takes its value, is at the closed dot, right, which is -3, right? -6 and -3 aren't the same number, right? So those two can't be equal to each other. And then finally, the limit as x goes to 6 of f of x equals 5. So I'm looking at the limit as x goes to 6. Well, we see we got a problem there as well. because if I'm approaching 6, right, if I kind of approach it from this side, it looks like I'm going to that value there at 2. If I'm approaching it from the right-hand side, that one does look like 5. So only one of those is 5. Right, and that's that last thing we talked about in our previous notes, right? That if the left-hand and right-hand limits aren't the same, that our values, then the general limit doesn't exist, doesn't have that value. So I can say, right, it's going to be false because the limit is x approaches 6 from the right of f of x. Well, that's 5, but the limit is x approaches 6 from the left of f of x. Right, that looks like it's going to 2. All right, and 5 and 2 aren't the same number. Okay. Okay. Okay, so in that example, right, I talked about a limit going off to infinity. And so let's let that be our next major topic, being limits and infinity. Right, or as I like to think about this, is really what we're focused on here with limits and infinity or asymptotes, right? 2 different kinds of asymptotes, right? And when we get to the second kind with horizontal asymptotes, we're really thinking about those as just one case of that type of limit and infinity. Right? But let's start with the other kind first, right? Our vertical asymptotes. They're a little bit easier. Right now, we don't have any a lot of tools quite yet for determining what limits are, and determining on them, aside from kind of looking at them and going what happens, right? Determining, we don't really have a good way to determine exact values, but we can use our intuition at least to help us think about things like we just did with that example here, with going from -2 from the right-hand side. All right, so let's kind of think about that and use that that type of problem as an example. Right, and so let's let our function f of x be x over x minus 2, and let's consider, right, the limits. Let's go what happens when x goes to 2. Right, now I can't plug 2 into the function, right? If I plug 2 into the function, right, f of x is not defined there, right? The domain of this function, right, is everything except 2, right? And so I don't exactly know what's happening at the function at 2, but if I want to, I can take my calculator and graph it, or we can use our intuition a little bit, and let's try to do that first. So if we want to talk about limits in general, right, it's a good place to start is to think about one-sided limits. So let's look at the limit as x goes to 2 from the left of f of x. In other words, the limit is x goes to 2 from the left of x over x minus 2. And now if I'm looking at this function and thinking about this limit, right, our limit is x goes to -2, right, what we kind of have happening, right, my number on the top here, well, I'm plugging in a number that's getting closer and closer to 2, right, and so this number here should be approaching my numerator. That's supposed to be the word approaching. 2, right? I mean, it's getting close to 2. 2 is a nice whole number. Plugging 2 in, this is going to give me back 2. And so, okay, my numerator is approaching 2. Not so bad. The denominator, on the other hand, right, has a little bit of a different scenario. I'm approaching 2 from the left-hand side. So I'm plugging in numbers that are just slightly bigger, slightly smaller than 2. It's like 1.9, 1.999, 1.9999, right? Numbers that are just a little bit less than 2, right? This is going to be approaching 0. Right? And if I'm plugging in those numbers that are slightly less than 2, well, if this is slightly less than 2 minus 2, like 1.9 minus 2, that's a negative number. 1.999 minus 2, it's also a negative number. Right? As long as I'm plugging in values that are slightly less than 2 and then subtracting 2, I'm going to get back something that's a small negative number, right? Approaching 0, right? But negative, or and negative, not really but negative. Now, in other words, my numerator is approaching a nice whole number, right? 2 is just a nice whole number. Getting close to 2 doesn't really cause any issues, right? But dividing by numbers that are really small, right? Dividing by a really small number is the same as multiplying by a really big number, right? That's what happens when we take reciprocals, right? If I take 1 over a billion, that's a really small number. But if I divide by 1 over a billion, right? Dividing by a fraction is the same as multiplying by its reciprocal. So that's like multiplying by a billion, right? And then I got 2 times a billion, which is a billion. But in this case, we want to make sure we're thinking about negative numbers, right? And so here we have 2 divided by something that's really small and negative. So that's going to look like 2 times something that's really big and negative, right? So this is going to be a big negative number, right? Big negative. Right? And we can represent that, right, by negative infinity. Because that number can get as big as we want, right? I can make it as big and negative as I want, right, just by getting this closer and closer to 2, right? Because as that fraction or that difference gets smaller, right, when I divide by that, once again, it's going to get bigger and bigger and bigger. Right? So I can make it as big as I want, and it goes off to infinity. Similarly, if I look at from the right-hand side, right, we got something similar but not exactly the same going on. Right, my numerator is still just approaching 2. Right, so this is approaching 2. Right, but my denominator now, if I'm plugging in numbers that are just slightly bigger than 2 and I subtract 2, what I get back is not negative anymore. Now it's going to be positive. In other words, this time I'm taking 2 and dividing it by really small positive numbers. So that's like when I think about that reciprocal again, right? That's like dividing by really small, dividing by a really small positive number is like multiplying by a really big negative. Start over. dividing by, right, small positive numbers, numbers that are getting close to zero from the positive side. It's like multiplying by big positive numbers. Right, so the sign doesn't change, right? But we think about dividing by something small, it's like multiplying by something big, right? And so this is like a big positive number, right, which we can represent as going off to positive infinity. Now we're going to need to do a little bit of work to make that more precise. Right? We're really going to need some what we call the limit laws in section 2.3 before that can be made super precise. But for right now, we can use our intuition to get an idea of limits, one-sided limits, right, and how those apply then with vertical asymptotes. All right, and that's really what we already used in that previous example from the one particular case. Now, the other type of way that we can have limits at infinity, limits and infinities interacting, we're talking about limits at infinity, right? And these are where we're going to find things like horizontal asymptotes. All right, so let's start off just like the last time with an example. All right, say we could look at something like the limit as x goes to infinity of x squared, right? And if I think about the limit as x goes to infinity of x squared, well, if I take a big positive number and I square it, I'm going to get back another big positive number. And I know what x squared looks like, right? I mean, x squared looks something like that, right? And so the more I go off in the positive direction, the further I'm going up in the y direction, the f of x direction. So we can say that that's equal to positive infinity. Similarly, if I looked at going this in the negative direction of x squared, right? I look at my graph and I go, okay, if I plug in bigger and bigger negative numbers, well, bigger negative numbers, if I square a negative number, it becomes a positive number. So squaring a big negative gives me back a big positive, right? And our graph kind of agrees, a graph agrees with that, going that looks like it's going off to positive infinity as well. We could do something else. Let's do a slightly different one. Right, what if I looked at something like 1 over x cubed? Now, if I plug a big positive number in and I cube it, right, cubing a positive number is still positive, becomes an even bigger positive number. Graph of 1 over x cubed, right, looks something that. And so this fraction, right, the numerator is staying the same. My denominator is getting bigger and bigger and bigger in a positive direction, right? So my numerator stays the same size and my denominator keeps getting bigger, right? The overall fraction is going to get smaller. And I can make it as small as I want just by making the denominator as big as I need, right? Give me an arbitrary value and I can just say, well, as long as I pick an x value big enough to where its cube turns the fraction smaller than whatever value you give me, right? I can make it fit our rough definition of a limit that goes to 0. right? Similarly, if I look at take the same function from the negative infinity side, right? Well, if I cube a negative number, it stays negative, right? If I take three negative numbers and multiply them together, it's negative, right? So that's cubing a negative, stays negative. But this is still, it's becoming a small fraction, small as I need. Yeah, it's negative, but that's all right. Just because it's negative doesn't mean it has a problem approaching zero. I can make it as small as I want. It's just approaching the horizontal axis, right, or approaching the x-axis in my graph from the left hand, sorry, from below rather than from above, right? And so that limit there is also going to be 0. Now, those aren't too bad, but what if we ask ourselves something slightly more complicated, right? What about, say the limit is x goes to negative infinity of, oh, let's write the square root of x to the 4th plus 3x cubed minus 7 over 5x squared plus x minus 3. Well, that one's a little bit harder for us to have any intuition about what's going on, because I can talk about what happens when I plug negative numbers in, right? And I plug negative number in, I take it to the 4th power, and that's a big positive, and so, okay, that's fine. Right? Well, but now that's a big negative, like, and then I take its square root, so I gotta really even hope that the thing under the square root's not a negative number, right? And then the denominator, I go, okay, well, I can plug a big negative number in and I square it, and that's still fine, but right, what's going on with the rest of the polynomial? Not too sure. And then once I take that quotient, it becomes even less clear, right? How do I determine how to calculate these types of limits? How can I get some intuition with these types of limits? And the answer is we need a little bit more theory. We need some more tools to help us answer these, right? What we can do at the very least is use our intuition to help us out and give us some things that we can start with, right? With limits in general and these limits at infinity to give us a place to start, right? And so that's what we want to finish this section with, right? And motivate ourselves or motivate the topics in 2.3, right? And so let's look at two last things, right? One of them, right, is kind of our big limit theorem that in some sense is not so big, but it's going to be a pretty important tool for us when we want to break down problems. Right? It's going to say, well, let's let C and K be constants. Then I know that the limit as x approaches C of a constant K is equal to K. And I know that the limit as x approaches C of the function x is equal to C. Right now, in each of these cases, right, we can't formally prove this theorem, right? I mean, well, we can formally prove it, but it requires us to know and to use a more precise definition of the limit that we have so far. But we can use our intuition to at least make ourselves believe that this theorem is true, right? So the limit is x approaches C of the function k, right? Function y equals k. That's all we're looking at. Y equals some constant. So let's pretend like k is equal to 5, right? I have the function y equals 5, right? That's just a nice horizontal line. So no matter what value I'm looking at, right, my function is always just saying 5. No matter how close I get to any particular number, all the function ever says is 5. So if I use that idea of approximating limits like we did earlier, right, and I build out that table, right, no matter what value of c I pick, when I approach it from the left, all my function does is say 5. All it does when I approach it from the right is say 5. And so from both directions, it's just telling me 5. And so my table would just have a whole column of 5s, right? And I go, well, where does that look like it's trending? Well, it better look like it's trending towards 5. Now, I said 5 was just an arbitrary number that came to my head, right? That same thing would work no matter what constant I had there, right? That function is always just all it says whenever we do those approximations is whatever value of k is, right? And so it shouldn't be too hard to believe, right? That the limit as x approaches c of a constant is just that constant. The second part of the theorem, right? The limit as x goes to c of the function x, right? That's the function we're looking at, right? Our f of x here is the function y equals x, right? And I like to think about y equals x as the echo function. Basically, whatever number I plug into it, I'm getting the same number out of it. And so if I approach c from the left, so if I plug in numbers that are just slightly smaller than c, so let's like pretend c is the number 7, right? So I can plug in numbers slightly smaller and like 6.9, 6.999, 6.99999. And the function is telling me back 6.9, 6.9, 6.99999. All right, so those values from the left look like they're going towards whatever my value is for C. And similarly, if I plug in numbers just slightly bigger than 7, so like 7.1, 7.01, 7.001, right? That's my function is telling me back those same numbers. So when I calculate the limit from that, from the left-hand side, right, it's also going to look like it's going to 7. So I'm going to C, yeah, from two different sides, but that's all right. We know how to deal with that with limits, right? Limits don't care what side we approach. They just care where we approach, right? And so the function y equals x, or the echo function, right, just going to give me back my value. Wherever I'm approaching in my limit, right, is going to be the value of that limit. A kind of related theorem is we can then take what we were looking at with those limits at infinity and extend that one a little bit further as well. Right, so if we want to think about limits at infinity and some simple functions, all right, let's let n be a positive integer, right? So I'm thinking about n as just some nice whole number, right? Positive whole number. That does not look like 4, look more 4-ish. We want to look at 4 different limits here, right? So one of those is I can look at the limit as x goes to infinity of x to the n. That's an easy one to start with. And what we want to be doing is kind of just generalizing what we looked at in our example here with these horizontal asymptotes, right? And so like this example with x squared, right? That's an example of x to the n, right? Just my n value is 2 in that case. And so we want to think about what happens in general. Well, no matter what exponent I put in there, right? No matter what whole positive integer exponent I put in here, right? If I take a positive number and I take it to a positive exponent, right? If I let that get bigger and bigger and bigger, right? It's going to give me back a bigger and bigger and bigger number that's still positive. Similarly, if I look at x to the minus n, so this time I'm really just focused here on these limiters as we go to positive infinity first. If I look at the limit as x goes to positive infinity of x to the minus n, so if I have a negative exponent, well, negative exponents are the same as taking reciprocals, so that really looks like 1 over x to the n. And if I plug in bigger and bigger positive numbers, this denominator here is getting bigger and bigger and more positive, right? Numerator is just staying at 1, so that fraction is getting smaller and smaller and smaller. And like we talked about in that last example, right, means that that's going to 0, because I can make that fraction as small as I want or as close to 0 as I want. If, however, we start looking at negative infinity, we have to be a little bit more careful. Because now if I take a number that's going to, or letting x go to negative infinity, so I'm plugging in bigger and bigger negative numbers, right? I have to be careful with my exponents, right? Because if I say square a positive or a big, if I square a big negative number, just like we did in the x squared case here with this graph, right? I get a big positive number back. But if my n value is 1 and just plug in back big negative numbers, well, my theorem up there says I should get back another big negative number. But if I square it, I get back a big positive number. If I cube it, well, cubing it, that's taking 3 negative numbers and multiplying them together. And I know if I multiply 3 negative numbers, I get back another negative number. And so in this case here, we have to be a little bit more careful and separate out our answer into 2 separate cases, right? I'm either going to get back a positive infinity, right, when n is even, because if I take a big negative number to an even exponent, I have an even number of copies of that negative number and an even number, if I multiply together, an even number of negative numbers, right? All the negative signs are going to cancel out to give me back a positive number. But if I have an odd number, I'm going to be left with one of those negative signs that I'm not going to be able to cancel, right? And I get back a negative number, right? And so when n is odd, right, that limit at negative infinity is going to go to, the limit as x goes to negative infinity of x to the n, it's going to go to negative infinity. Right, and if once again, if we looked at putting in negative exponent in there, so x to the negative n, right, I can use the fact that that just means writing a reciprocal, right? And now, well, my numerator is staying just 1, just like it did above, right? The only thing that changes is our denominator as we go to negative infinity. And in both cases here, these numbers are going off to, they're becoming bigger and bigger. One of those is becoming bigger and bigger in a positive fashion. One of those is becoming bigger and bigger in a negative fashion. But they're still becoming bigger and bigger. And so I can make this fraction as small as I want, right? When n is even, it's going to be a small positive number. When n is odd, right, it's a small negative number, but it's still as small as I want, right? As small as it can make it, right? In that case, right, we're going to go to 0, no matter whether or not n is positive or negative, right? So that's like this example here with the x cubed, right? This is a odd exponent, right? And so I'm approaching my horizontal asymptote here at 0, right? From the negative side, right, if I had an even exponent, it would just approach the positive side, right? That's really the only difference, right? Which we can see by graphing the function, right? Why our calculator or using other tools. So, anybody have any questions, comments?
I don't have a question on this, but I do have a question on the homework.
Okay, so I'm going to take a break, and then when we come back, we can answer that question. Is that all right? So yeah, when we come back, I want to start 2.3, but I also want to give you guys a chance to, if you had homework questions and stuff. So that'll be a good time. Why don't we take a 7-minute or so break? Actually, let's do like 10 minutes, because I've been talking for quite a while. So like